Okay, the next session is a bit unusual. We're going to have a panel discussion led and moderated by Clifford Johnson and devoted to the impact of D-branes. And it's quite appropriate that Clifford, who was postdoc here at the KITP during the D-brane revolution and greatly impacted by it, should help moderate and run this panel on the impacts of D-branes. So there will still be time for questions and interactions with the audience at the end of this. So Clifford, take over.
Thanks. We can give that extra one to. I guess it was switched on. Well, hello everyone. I hope you can see us. So. First, let me say it's a real pleasure to be here. This is sort of like a high school reunion or something. Really wonderful, especially when we all got off the school bus from the hotel. And I'd like to thank the organizers for inviting me to chair this. What I thought we'd do is have a moment of reflection, where we've been, where we are now, and there'll be at least a call to Steve's session later on when we'll talk more about the future. But feel free to talk about that as well. But what I'd like to do mostly is sort of reminisce and with some particular subjects in mind. And the idea was to have some people up here who can speak to some sort of roughly divided areas in the field that were heavily impacted by D-branes. Of course, there's a lot of crosstalk between these areas, which is why D-branes and Joe's work was so wonderful. To my mind, when we talk about the revolution that happened in the 90s, it's usually referring to what's called the second superstring revolution, and that was, of course, a wonderful thing. But I actually think there was more than one revolution in some sense. At the same time, we just had this complete change in our thinking about lots of things, whether they were to do with string theory or not. And I think the connective tissue, for me, really was Joe's work on D-branes, which really sort of taught us how to rethink all kinds of interesting field theories and weird corners of the field that were pulled together by this connective tissue. And so that for me, was the actual bigger revolution that's actually still happening. And as I write or lecture about D-branes from way back, my joke was always that the D-branes were the heroes of the revolution. I've sort of rechristened them now to be the tools of the revolutionary, and Joe, in some sense, was that or is that revolutionary, and those were his sharp tools. And so it was a bloodless revolution, I hope.
The conference isn't over yet.
The conference isn't over yet. But anyway, so of course, some of the things we were struggling for were new handles on how to compute, how to count, new degrees of freedom in various regimes of various theories. And D-branes sort of came along at just the right time. I remember my time here. I came along at just the right time from the institute to this institute, just when the explosion had already begun, but I was just about arriving in time to take part in helping sort of spread the word about D-branes and do some of those early calculations that showed what they could do. And then, of course, there were the notes. There was just this sense that I and others had that this is going to be really important. The whole field has to know about this. This language has to be sort of gotten out there and sort of cleaned up and become sort of universal for us all to talk to each other. And so that was what was behind encouraging Joe to very patiently allow us to help him write some notes that could go out there. And that, of course, as you know, turned out to be extremely useful for bringing the field all on the same page with regard to the language and techniques and so on and so forth. So I don't want to spend too much time talking. I think I'd like to defer to my colleagues who are going to, in turn, and you can pick who goes first, etc., just say a little bit from their nominated corner of the field, what the perspective, or what the changes that D-branes brought look like from those corners. So I have Andreas is going to talk about impact on aspects of field theory and both formal and applications and so on and so forth. Greg will talk about mathematics, mathematical aspects, both in physics and in pure mathematics. And Samir will talk about aspects of quantum gravity, particularly ongoing research in black holes. So I'm going to shut up now. I'm going to say thank you for Joe for being a wonderful postdoc mentor, very kind, and took me very seriously and helped me really find my voice in the field. And happy birthday.
Thank you.
So who wants to go first?
The green light is on. Okay,
Yep.
now it's working. Okay, so Cliff asked me to say something about the impact of D-branes on mathematics. So I come to present the D-branes viewed through the lens of mathematics, not to praise them. Other speakers will bestow the richly deserved praise. So I think if you computed the expectation value of the influence of D-branes over the ensemble of mathematicians, it would actually be pretty small. But if you restricted the ensemble to mathematicians who work on geometry, topology, and representation theory, and if you weighted that average by the quality of the mathematician, then I think you would get a very strong signal. So I'm going to restrict my comments to D-branes per se, which is unnatural because, of course, they're so closely connected to other solitons and other aspects of physical mathematics. And I draw a distinction right at the beginning, which is that D-branes have let physicists understand much, much better pre-existing mathematical structures. And then D-branes have also created new mathematics. So a good example of that would be the ADHM construction of ADHM construction of instantons and the NOM construction of monopoles. And I don't know if you tried to study that subject before D-branes, where the hell did these big matrices come from and why should that have anything to do with instantons? And then you look at the D0, D4 system and it's completely transparent. But then you put the branes at orbifold points and you explain Kronheimer-Nakajima's construction of instantons and ALE spaces, and that's explaining pre-existing mathematics. But then the physicists, of course, bring a completely new point of view to the subject and have led to a great deal of new insights in monopoles, instantons, quiver varieties, quiver representation theory, and so on. Now that's just one instance. And so looking at the subject more broadly, and Clifford asked me this, I could think of at least 5 broad areas where D-branes have had a very profound influence on mathematics. And to help you and me follow the train of thought, I think I'll write them on a board. So one would be duality symmetries, D-brane categories, with the emphasis on category, sorry, Joe, and extended field theory. extended means you recognize the importance of line defects, surface defects, and things like that. A second, and of course these subjects are very closely connected, is non-commutative geometry. And of course the physicists both understood better the previous work, but then came back and made some very significant contributions to that. A third would be twisted K theory and what's called differential K theory, which is the proper home, at least from a mathematical point of view, of Ramon fields. And that was started by Joe's observation that the D-branes source Ramon fields. The third is analytic number theory. Now that's, of course, a huge topic. So let me be a little more specific. You see, of course, D-branes led to the Strominger-Vafa program of accounting for black hole microstates in terms of coefficients of certain automorphic forms. So the asymptotics of Fourier coefficients of automorphic forms is one aspect of number theory. Another is Rademacher summability. And a third, most active now, is the subject of what are called Mach modular forms. This is all an outgrowth of D-branes. And finally, through F theory, we have the algebraic geometry of elliptic fibrations, which of course is an old and venerable subject in algebraic geometry. But a lot of work was stimulated by the desire to make F theory models and so on. Okay, so let me just finish up and say in this subject, which is huge, there are two very big outstanding contributions to mathematics, and that is Kontsevic's homological mirror symmetry, and the other is Kapustin and Witten's interpretation of the geometric Langlands program, which has had just an enormous influence in what's called geometric representation theory. Maybe that's a cue to stop. Okay, so I'll leave it at that.
Thank you, Greg.
So your presentation reminded me actually of a thought I had during Strings 96, which was the first Strings after the D-brane paper, and you were speaking. And after the D-brane paper, I started to get a lot of citations, and sometimes I'd be cited for things I hadn't done first. Sometimes I'd be cited for things I hadn't done at all. But you were the first person to cite me for something I didn't even understand.
Well, I had a lot more to say, but there's something I just can't resist, which is that, apropos of this non-commutative geometry, I was hunting around, and there's a series of papers by Liu and Yao, which refers extensively to the Grothendieck-Polchinski ansatz, and a stranger pair of bedfellows cannot be imagined.
So who wants to go next? Okay. Andreas.
I was very pleased when I got the email from Clifford to be on this How D-branes Changed My Life panel. Since it certainly had a big impact on my career when I started out as a PhD student in '97. the D-branes were already very much all the rage, and while all my peers around me, they were calculating high loops in the standard model, trying to understand field series order by order and perturbation theory, I was drawing little stick figures on pages with NS5 branes and D-branes in between them, and I was claiming I can understand field series even non-perturbatively. I can get all their moduli spaces, all the BBS spectra just by doing these simple stick cartoons. And I managed to write papers like this, which is still amazing these days when I tell my students that they actually need to do hard work. When I remember back then, what our first papers looked like, that was a different world, and it was certainly all due to D-branes. And then things, of course, got better for people who wanted to use D-branes to study non-trivial quantum field series. Once ADS-CFT came along, no D-branes, probably no ADS-CFT. And I was a little late of joining that bandwagon, but ever since I started doing ADS-CFT, I've never left it anymore. In the beginning, I think the early days of ADS-CFT, people were always trying to, let's really understand it better, let's understand how it would look like small lambda, small n, and then we can go apply it to the real world and maybe learn something about the field series we really care about. But so starting 2002 or so, when Son calculated the viscosity, I think people thought, we're never gonna get small n, small lambda right. Let's just take what we have, take ADS-CFT as we understand it at that point, and see what we can learn about the real world. And it has been a really great thing ever then. For me, D-branes came then back a second time when I wrote my paper with Army Katz on the flavor branes, where we didn't just take ADS-CFT, which came out of D-branes, but we threw in D-branes one more time on top of it. And I thought this was sort of one-time paper, and then I do other things afterwards, but somehow they always come back to me. It's no matter how hard I try to run away from the flavor branes, there's always something else to do. Somebody asks me a question, and I write just one more paper on flavor branes. This way I also ended up actually writing my first paper with Chloe ever, because these flavor branes came back to me. I worked with Shamit on something about flavor branes. Eva worked with Chloe, and then at some point we decided to throw the papers together and wrote something about making a lattice of flavor branes in the background of D-branes. It was all D-branes all over. But maybe since I'm supposed to highlight the big successes that D-branes have had, so let me remind you about all the good things that people have done with ADS-CFT. Right? It's sometimes there's this attitude that because we can't do things precisely, right, we don't have the ADS-CFT tool to QCD. Maybe what are you doing? Trying to apply things to the real world, isn't this all kind of sort of some fake? But there are a few good things that have come out of this that I think clearly have advanced the field, where people took ADS-CFT as sort of a starting point to learn some qualitative lessons about how strongly coupled field series work, and then applied them to other systems. The highlight is still eta over S being 1/4 pi. I think that's sort of this benchmark value. You can't go to a talk about Wick experiments anymore without seeing somewhere a plot where there's a horizontal line of eta S equals to 1/4 pi. They somehow didn't get the message yet that it's not a bound. All experimentalists would tell you, 1/4 pi is a bound, but I think we can forgive them that. Since we needed ADS-CFT to even actually understand that it's not a bound by constructing explicit supersymmetric gauge series whose gravitational dual has a viscosity which is below that. But then the other thing that happened recently is these anomalous transport coefficients, where people starting from ADS-CFT found that there are new transport coefficients in hydrodynamics, which Landau and Lifshitz forgot to write down. Most of my Russian colleagues think that could never ever happen. This is sacrilege even to kind of contemplate the idea there's something that's not in Landau and Lifshitz. But people found those in ADS-CFT. But I think by now we have a complete understanding within field theory. People don't need to talk about ADS-CFT anymore. They can calculate these transport coefficients using triangle diagrams. But this whole structure wouldn't be there, or presumably wouldn't be there yet hadn't it been for these initial calculations by the groups in India and in Munich of these what's now called the chiral vortical effect. These new transport coefficients that are there in any gauge theory that has some sort of triangle anomaly. I also like to highlight the energy loss calculations. That's something I spend a lot of years of my own life on in ADS-CFT, where if you calculate energy loss in a strongly coupled theory, you find behavior that's qualitatively different from what you do with weak coupling. If you calculate energy loss in QED or QCD in any perturbative field theory, you get a coefficient that depends on diagrams, and you can calculate loop corrections to it, and you can do a lot of work. But then you always find that, say, the stopping distance of a particle goes like energy to the halves power, no matter which weakly coupled field theory it is. and no matter how many loops you calculate. But if you start with ADS-CFT, you find that stopping distances don't just modify. It's not just the prefactor that gets modified, but the actual power law changes, and it changes in ways that now depend on details. But if you want to have some sort of diagnostic of whether an energy loss of a partner traveling through a medium is governed by weak and strong coupling, now ADS-CFT gave us a tool of even how to address this question by saying, well, look for the power laws. How does stopping distance scale with energy? If it's not square root of E, then you have some system where energy loss is intrinsically strongly coupled. And I hope there's way more along those lines where you take these toy models that ADS-CFT gives you and trying to extract lessons for the real world. I think non-relativistic systems is something where we hopefully will see much more happening in the near future. I think topological phases is something many of us have been dreaming of, that we maybe get some handle on them using D-branes, where there are a lot of qualitative questions there. Non-Fermi liquids, there was some sort of mini growth industry using ADS-CFT for understanding those even. So now people also went back and have some use again field theory techniques in order to basically extract the lessons that came out of ADS-CFT. I think this is something we can do these days already without going to small n, small lambda. We can use ADS-CFT as a toy model, get qualitative insights from there, and then go back in and kind of say, now let me do field theory honestly and kind of try to implement what I learned from ADS-CFT. Yeah. Thank you.
Okay, maybe I find it easier to stand up because then I can see the people all the way to the back. So I've been working with black holes for a long time, and from the perspective of somebody who works in that field, the impact of D-branes has been, as you probably all very well know, completely phenomenal. So just compare how life would be if we were not using string theory and D-branes, which is how things were maybe in the early 90s. And I remember working in black holes at that time and on the information paradox, and things were so dry. All you can do is stare at the Schwarzschild metric, and the only tool you have is that you can have quantum fluctuations, and if the fluctuation at the Planck scale, something happens, okay? And we don't know what happens. And that's it, and you keep staring at this over and over, and you have the information paradox, and nothing moves. It's like trying to squeeze water out of a stone. And many of us spend countless years trying to beat our heads on it, and just compare to how rich things are now that we have all the tools of string theory. So starting with the early works of Susskind and Sen and Strominger-Waffa, who used D-branes to tell us how a black hole could be modeled, we now have so many tools. We can actually know what we could be doing. For example, you can go to weak coupling, you get a theory of intersecting branes, you can actually count the number of states, and you get the Becquerel entropy of the black hole. It's so phenomenal. There are relativists today who still do not want to use string theory for black holes. And I feel very sad when I see that, because here on one side you have a complete tool where you have a theory where in principle you know what to do. If somebody gave you a big computer and you put the whole problem in there, the answer would come out. And the beautiful thing is that in string theory, after we have D-branes, the theory is sort of complete. We know we can't add any more particles. There are some particles for every charge, and you can't add another kind of brane or change the property of a brane or the tension of a brane or the coupling of a brane. It's such a wonderful thing to have a theory in which there are no free parameters, because you know whatever you're doing is, assuming this whole structure is correct, is it. There's nothing to change. There's nothing to tune. And I think I found it really very beautiful. Everything you try with black holes, like the entropy calculus, Strominger and Waffa jumps and just works on the dot. So it's been absolutely wonderful suddenly to have all these tools which can tell you how to tackle the deepest questions, because you have the theory and all you have to do is to extract the answers. So I think that's been an absolutely big revolution, which takes us to the deepest parts of what we would like to do with black holes, or even with other things which we are just barely beginning to understand, like the early universe. I would still say we have the theory, and the theory is string theory. The main tools are D-branes with its couplings and so on. Just go to high densities and figure out what to do. It's a technical problem, not a philosophical problem. So I think this is the enormous beauty of things that we have learned here. For my own part, one part of the work which I've been doing for the last so many years started off with a paper of Horowitz and Polchinski, where they're worried about how a string at weak coupling becomes a black hole if you slightly increase the coupling up to a critical point. And in fact, I was reading that paper and trying to struggle with how the transition exactly would happen. And I remember that's the time when we found the transition actually is not smooth. It's actually a phase transition. And once you cross the coupling of the Horowitz-Polchinski point, the bound state of strings actually starts swelling and swelling, and that's what led to the whole fuzzball thing for us. So in fact, a lot of things which Joe has done with D-branes and also with black holes have been at the root of all the things that we've been seeing with black holes today. At the end, let me say a few things about what Joe has been doing over the last couple of years and all the work that followed from AMPS. I think it has been truly remarkable in how many people have been brought together again to think about this crucial problem for black holes. So far, everybody, it seems, over the last few years had been doing their own things with black holes and was completely happy in what he was doing. So in some sense, everybody was happy, right? Everybody was having their own theory and it was working for him. And when they met, they all shook hands and said, yes, it's all working. But they were saying different things. So with the work of AMP, somehow everybody was sort of forced together to come in and sort of beat their heads together and say, okay, what exactly are we saying? And it seems to me that things have really been quite well focused into three camps. And let me just try to make this kind of a rough summary of where I think the field stands after all the intense work that the AMPS people and their collaborators put in from here. So there are people in the relativity community who thinks information doesn't come out. So then you have to do nothing. It all goes and gets locked in remnants, and okay, that's one answer. Because on the second side, you can have people who want information to come out, but they're willing to use scales where the physics is to be altered, find some effects on the scale r equals to m, the Schwarzschild radius. So something happens on that scale. For example, the work on fuzzballs talks about tunneling into some states, but all the physics is on the scale of 2m. And then you change something and you move on. And then the third set of things which has come out is that you change nothing on the scale m, you get a complete vacuum at the horizon, but things change on a scale which is now being called the page radius, m cube, which is the distance to which the Hawking radiation goes out. So for example, you could be having wormholes connecting the inside of the black hole to the radiation quanta. So you're changing physics in a fundamental way. Or the Papadodimas-Raju kind of construction where you try to say the quanta at infinity are not really independent of the quanta inside. And so I think the AMPS experiment has made this thing, thought experiment has made this very precise. They've really asked, as you fall into a black hole, if you try to measure entanglement of a pair of things, do you get them correctly entangled as per the vacuum or no? And with that precise question, if you say they are not correctly entangled, you find physics on the scale m and you change something. And if you say they are correctly entangled, it is the vacuum, then you either assume that you get remnants or you look for physics on the scale m cube. So I think this has been very remarkable for a field which has been known for the amount of confusion, the amount of different ideas, to be able to actually put things into different categories so that now we can really sit down and see, where are the effects that distinguish all of us in different ways. So let me just close by saying one thing which truly amazes me about Joe. It's the number of emails he can write. So there was a time when we were, when the AMPS paper came out, we were spending all our time just every day going over the paper and saying, could this argument be right? How do we bypass that? How do we go around this? And so on. And I would send him an email. And the answer would come back the same day. So we got this impression that in Santa Barbara, Joe's doing nothing but sitting there all day and replying to our emails. Well, that's what we were doing on the other side. I and my postdoc would sit down and we would spend half a day composing an email, send it over to Joe, and a reply would come. Now, when I came back to Santa Barbara, I found there were about 100 people, and each had the same experience. So apart from all the work that Joe put in, I think he has put an enormous amount of energy into the field of black holes over the last year. And it's the amount of energy of talking to so many people, putting all the ideas together, answering all their emails, taking the effort to learn what everybody's saying. In this field, usually people don't listen to anybody else. But Joe actually listened to everybody. He seems to know what everybody's doing. And I think that's what helped to bring people together and advance this field a lot at this stage. Thank you. Happy birthday, Joe. Yeah.
Well, first of all, thank you to Greg, Andreas, Clifford, and Samir for your recollections. And yeah, I actually do have an inbox of about 2,000 messages related to this sort of. But the truth is, I decoupled from that email with you at some point, and you and Don exchanged approximately 100 messages in each direction. I think actually Don, even more than me, is kind of the hero of carrying on extended conversations to get to the. Maybe with less people. Anyway, but so D-branes was kind of a strange experience for me too. It was just kind of a curious. I had no idea where this was going. It was just a curiosity. It was kind of fun to do this one loop calculation and see things come out cleanly. Then what was the amazing experience was what happened after I put the paper out, because within 2-3 weeks I just completely lost control of this. I mean, Ed Witten, Greg, Mike Douglas, Ashok Sen, Andy, Kumran, Juan, Ego. I mean, just there was such a flood of things which, I pulled the dike out of the dam. But I if it was, if it was left to me, I would have probably gone on and tried to find them in a heterodox string or something. I had no idea where this subject was going. So it was just a remarkable experience, and thanks to everyone for developing it.
So we're going to open it up to the floor. Anyone who wants to reminisce about D-branes or ask questions of the panel, I think.
Before we do... Oh, all right, takes it. Well, I have two anyway. So. Before we do that, I just want to say, one of the things that always struck me about your papers in those days, when there was a lot of sort of people reaching in the dark, and this is kind of equal to this, is there are a lot of twiddles. This is sort of kind of equal to this. And your papers all had equal signs. It was just sort of, it was this. Sometimes arrows, yeah. But the fact that we had this precise, these numbers, these were the numbers, and now we could build everything out of just counting these numbers, and that for me was magical. And then there were times when the D-branes themselves just seemed sort of alive and sort of smarter than all of us, and it was all because you got those numbers right. It was fantastic. Maybe to set up the discussion. Yeah, I can point to people. We'll set up the discussion and maybe set up the discussion about the future. One of the things that I remember having gone through a previous phase some years before with matrix models was when Steve pointed out that in some sense we had early signs of what the D-branes were from back then, the instantons and so on and so forth. And that led me to think, and I still think about this time we were in when we were reaching for things. We needed new variables, we needed new degrees of freedom. It wasn't clear what they were, but in retrospect, we could see what the signs were. And then Joe sort of pointed it, shone a light on it, and then, as you said, it sort of just expanded. And I wonder if we're maybe coming to a stage like that. I have no idea, but it would be interesting to know if anyone has any thoughts about what might be the next D-branes. Are there signs where we're looking for something to fill a gap, and maybe we're getting some clues as to what they are? So anyway, at that point, I'll just throw that out, or reminiscences, or however you want to do it. Raise your hand and wait till the microphone gets to you.
Yeah, I remember when I first heard about the D-branes and the connection with the dualities. I think I was at Princeton. And the thing that struck me, and it still strikes me, it was a sort of philosophical thing. It sort of pulled the legs out of what we usually call reductionism, that at the bottom of things there's one fundamental set of degrees of freedom, and that's it. Once these D-branes were there, and you could move around in moduli space, and a D-brane became a fundamental string, and a fundamental string became a D0 brane, and D0 branes became 11-dimensional gravitons, and so forth. I began to get the sense, one of two things. Either these things are simply not the fundamental degrees of freedom, or there are no fundamental degrees of freedom. I still don't know which is right.
Thank you. Any other thoughts? Oh, Eva.
pointing or raising your hand?
If there's somebody else, they should
Go for it.
first. Well, this isn't a reminiscence about D-branes per se, but the question of what are we missing that's right in front of us? I mean, Joe pointed out that and his collaborators that, taking seriously the endpoints of open strings made these theories that seemed totally irrelevant and disconnected part of the story. And, this is something I've harped on for years, but I just think string theorists tend to focus on flat space-time geometries way too much. So my guess for what we're missing that's right in front of us is curvature, negative curvature in particular. All this focus on Calabi-Yaos and supersymmetry and so on seems to me a very strange and narrow focus for the field. And it's just a guess, but.
Thank you. Come on, people, go crazy. We've got 10 minutes.
All right. So I think Joe will excuse me because I always had crazy things to say, so it's okay. I agree with this assessment that of Eva's that in some sense we have always focused too much on space-time interpretation and wanting to connect to effective field theory. That's understandable because we would like to explain the standard model.
And Joe taught us to do that.
And Joe told us exactly how to understand normalization group and so forth. But I always felt that strings are much richer than that. I guess I would be parochial to say that Rob and myself and Laurent has been working on something called phase-space string theory. But it just goes back to these observations of T-duality or non-compact T-duality of Maldacena or Dardai or what people are trying to do with double geometry, that in some sense string theory does not really call for space-time interpretation. It is a very special interpretation. It lives actually in something that looks like a phase space. Perhaps it's something even richer. And that there are many, many things to explore that simply maybe don't lead to effective field theory interpretation. That was a narrow focus. And hopefully by broadening that focus, maybe making sense of this phase-space interpretation, we will have an opportunity to push beyond what Joe taught us in the 90s.
I'm going to stand on this side of the room to encourage this side of the room to get involved. I'd also like to say, you don't have to throw out wonderful thoughts about what may happen, but you should, homework through this whole 2 days is that you should maybe bring some of that to Steve's discussion at the end of Friday. Anyway, that being said, this side of the room, comments, reminiscences, thoughts? Yes.
So those that know me are shocked to see my hand up, given what the panel discussion is about. And Joe's work on D-branes actually had very little influence on my research, but something else did, and it's not something that people know because it's not associated with a publication of his, so I thought this would be an opportune time to mention it. So this was a long time ago, before the days of email. One day I get a phone call from Joe, and it's very unrelated to what he was thinking about. He was already into string theory, and he says, "Hey, Mark, inside a hadron with the B quark, it's kind of heavy. Shouldn't there be something you can calculate legitimately with QCD?" And I said, well, let me think about it a little bit. So that phone call had a lot of influence on my career for about 10 years after. And at one point, I called him back and said, hey, after I thought about it for a while, hey, Joe, there's a lot of interesting things here. You want to collaborate with me on this? And he said, oh, no, Mark, I've got other things to think about. Anyways, I'm very grateful to that, for that, and it's a pleasure to be here to help you celebrate.
So actually, that was the year I started my book. The reason I wasn't able to work on that was because I was writing my book. And Steve Weinberg always says he regrets writing his gravitation book because if he hadn't written his gravitation book, he would have proved normalizability. Well, if I hadn't written my string theory book, I would have worked on heavy quark physics, and I've always regretted that.
Anyone else? Eric.
Yeah, I was going to keep that for later, the student experience, but since this is a history of D-branes, and I really wanted to get a dig at Mark here. So I was just starting out with Joe, and there'd been Steve's paper on these 1 over lambda effects, and Joe was really interested in what can we use matrix theory to get to these things. And he had this intuition that the D-instanton would be the thing to do it. So he took this like first year grad student, gave me this like demented draft of a book, and told me to compute this D-instanton. I think it took us at least 6 months to realize there's actually a dilettante background that needs to be put in there. And I think one of the first papers I had to dig through had an author named Mark Wiseman on a disk calculation. So Mr. I don't have anything to do with D-branes was in the early days of all this. And so we worked on this, and Makoto was really helpful in trying to, and we were kind of stuck. But the good thing was I had to go through all the calculation he did with Rob, and we went through all the disk instanton stuff. I think there was actually a typo or something. You guys can look it up. So he was all prepped to go, and then the 95 friends came along, and I think those two things really clicked. So it shows that there's a certain serendipity to following your own intuitions.
Was it someone? While you're thinking, and in the closing minutes, I'll just mention. I mentioned to my wife Amy that I was coming up to chair this session, and she immediately, because sort of comedy is her thing, started making brain puns. And so I was coming up to see all the brainiacs and things like that. And I said, basically, we thought of all of the puns you can do with brains long ago. And there was even one on I think, Igor's slides earlier. So in the spirit of us doing, in the old days when we did silly things at conferences quite a bit, including silly dances and songs and things like that, feel free to start collecting all the various puns, brain surgery and brain scans. And there must be tons of them. I've never seen them all put together in one place. So, I don't know, send them along to me.
Sorry to keep breaking into the conversation, but I keep being reminded of things. Two things. I actually never thought about. I don't think in terms of puns, so it never occurred to me that there was a pun. The first person who made a brain pun to me was Tom Banks. Is Tom here? No, but he pointed out that somewhere in my first the 95 paper I wrote, you'll notice that we have 2 extra brains. Anyway, and so he I forgot there was this prehistory. Eric mentioned that he was working on D-branes before 95, and of course Jindai and Rob Lee and I, around the same time as Peter Harava and Mike Green, stumbled on their early history. And actually, one of the reasons for that early history was we were stuck down there in Texas. We weren't in Princeton. All the cool people in Princeton were working on the heterotic string, and we needed something to do. And nobody had really messed with the open string, and so it was a good way to keep my graduate students from bothering me. Was go calculate this open string thing, and there was some value to not being at Princeton at the time.
And that's why the notes, I think you had said this, were sort of also remedial lectures for the heterotic string generation, because no one knew that language anymore. So
we thought we got rid of open strings forever. Okay, I think that brings this lively panel session to an end. And our next speaker is Matt Strassler.
Yes. Hi, Matt.
Who is from, from nowhere?
That's more or less right.
Sorry?
That's more or less right.
That's more or less right.
So we need to lower the screen again.
And, but in any case, it's great to see Matt again, here especially. And he's going to talk on strings from things and things from strings.